Detection of autocorrelation. There are four methods to detect the autocorrelation in a regression model. First is von Neumann ratio, second is Durbin-Watson method, third is graphical, and fourth is run method. Residual ET is the estimate of the disturbance term UT, that is UT cap equals to ET. Von Neumann ratio, it is defined as the ratio of mean square of successive difference of estimated disturbance value. It is the ratio of mean square successive differences of estimated disturbance term to variance of estimated disturbance value. Mean square, it means ki divided by n minus 1, and summation, differences of estimated disturbance term, so et minus 1 to the whole square, and summation we will take to the variance of the disturbance term, it is divided by n, and summation et minus e bar to the whole square, which is del square by s square, that is, so del square by s square equals to n upon me n minus 1 into summation t takes value from 2 to n et minus 1 to the whole square by summation t from 1 to n et square, since e bar equals to expectation of et equals to 0, that is von Neumann ratio VNR equals to n by n minus 1 summation t takes value from 2 to n et minus 1 to the whole square by SSC, it will be SSC summation e square et square, sum of squares of error, error sum of squares, which is residual sum of squares as well, SSC. So for large n VNR, von Neumann ratio, which follows normal expected del square by s square, comma variance del square by s square. So expectation del square by s square equals to 2n by n minus 1, and variance del square by s square equals to 4n square in bracket n minus 2 by n plus 1 n minus 1 cube. Formula is true only if residuals are independently distributed. But presence of autocorrelation, residuals not independently distributed, not applicable. And this formula is not applicable testing of autocorrelation for small samples when n is less than 30, then this von Neumann ratio is not applicable, while it is applicable only if the residuals are independently distributed. But presence of autocorrelation, residuals not independently distributed, so it is not applicable in the testing the autocorrelation for small samples. Durbin-Watson, it is applicable for small samples. Since von Neumann ratio was not applicable testing of the autocorrelation for small samples and less than 30, so Durbin-Watson is applicable for the small samples, and it is appropriate only for the first order auto regressive scheme. ut equals to rho ut minus 1 plus vt, where vt is the error term, and residual et is the estimate of the disturbance term ut, that means vt cap equals to et. We wish to test the null hypothesis h naught rho equals to 0, u rho equals to 0, since covariance term equals to covariance x for this ut comma ut minus s, which is which is gamma s equals to rho to the power s into sigma square u. So it will be 0 when rho equals to 0, means covariance will be 0. This means no autocorrelation. So null hypothesis is that H naught such that rho equals to 0 means no autocorrelation. UTs are not autocorrelated with the first order scheme since it is AR1 autoregressive scheme first order. So it says UTs are not autocorrelated with the first order scheme against the alternative hypothesis H1 such that rho equals not equals to 0, that is H1 UTs are autocorrelated with first order scheme. And the DW continue. We use the Durbin-Watson test. Durbin-Watson test statistic. D equals to summation T takes value from 2 to n UT minus UT cap minus UT cap UT minus 1 cap whole square by T takes value from 1 to n UT cap square, which is equals to T takes value from 2 to n ET minus 1 to the whole square by summation T takes value from 1 to n ET square. T equals to 2 to n ET square plus ET minus 1 square minus 2 ET minus 1 by summation ET square. For large n, T takes value from 2 to n ET square is approx equals to summation T from 2 to n ET minus 1, which is approx equals to summation T from 1 to n ET square. So it will be summation 2 times summation T takes value from 2 to n ET minus 1 का whole square minus 2 summation T takes value from 2 to n ET into ET minus 1 by summation T take value from 2 to n ET minus 1 square, that is D equals to 2 times 1 minus rho cap, where rho cap equals to summation ET into summation T from 2 to n ET into ET minus 1 by summation T from 2 to n ET minus 1 square. From this rho cap equals to 0 gives D equals to 0, D equals to 2. From this, when rho cap equals to 0, it gives D equals to 2. And if rho cap equals to 1, it gives D equals to 0. And if rho cap equals to minus 1, it gives D equals to 4. So, when rho cap equals to 1, that means D equals to 0, it shows the perfect positive autocorrelation. And when rho cap equals to minus 1, that means D equals to 4, it shows perfect negative autocorrelation. So since rho cap from 0 to 1 gives D from 0 to 2, there is positive autocorrelation. And since rho from minus 1 to 0 rho cap gives D from 2 to 4, there is negative autocorrelation. dl and du is the lower and upper limit suggested by Durbin and Watson set of 5 reasons for the value of D. There are set of 5 reasons for the different values of D. We will make the graph. Reason dl to du to 4 minus du 4 minus dl in at x-axis and comma the last point is 4 at x-axis it represents D, and at Y it is FD. So from the region, this region DL, from DL to DU and 4 minus DU to 4 minus DL is the uncertainty region, and from DU to 4 minus DU is no autocorrelation, means except H naught. And from 0 to DL and 4 minus DL to 4 is reject H naught. At the from 0 to DL, it shows critical region for autocorrelation, and from 4 minus DL to 4 it shows critical region for negative autocorrelation. From this, it is evident that first, if D is less than DL, that means we reject H naught and accept that there is positive autocorrelation. And if second thing, if 4D, if D is greater than 4 minus DL and less than 4, then it reject H naught, except that there is negative autocorrelation of the first order. Third, if D is greater than DU and less than 4 minus DU, it accept H naught, that is of no autocorrelation. And fourth, if D between DL and DU, that means between DL and DU and between 4 minus DU and 4 minus DL, then the test is inconclusive. And the relation between Durbin-Watson statistics, D, and von Neumann test, VNR. VNR equals to small n by n minus 1 into D. So Durbin-Watson C cap equals to 9.02 plus 0.93 YT, where Y are ET and ET minus 1. ET have given 0.6, 1.9 and minus 1.8. ET minus 1 means first is no and second is 0.6 and 0. ET minus 1, and after taking its square, and at last we will take ET square and summation all of them, then D will be T takes from 2 to n value ET minus 1 to the whole square by summation ET square. N equals to 12, alpha equals to 5% for one explanatory variable. DL equals to 1.09 and DU equal 1.36. So critical region, if D from 0 to DL and from minus 4 minus DL to 4, then it will be the critical region, means reject H naught. Acceptance region will be if D from DL to DU and from 4 minus DU to 4 minus DL. That is no inconclusive reason. That is inconclusive reason. Acceptance reason is from DU to 4 minus DL. Graphical method. Graphical method. Residuals are spotted against the time. In the graphical method, the residuals are spotted against the time, means ET, where T is the time and ET is the residual. The time sequence plot exhibit the time sequence plot exhibit any pattern, then autocorrelation is present. And if time sequence plot does not exhibit any pattern, then autocorrelation is said to be absent. Figure A, Figure B, Figure C, Figure D, and Figure E. Since Figure A, Figure B, and Figure C, Figure D, Figure D have no pattern, Figure B, C have a pattern, and Figure E also don't have pattern. Where at x-axis we are taking t and at y-axis et, which is ut cap. And figure A, it also take a pattern. So starting two figures are in having exhibit a pattern, so there is presence of autocorrelation. But last two figure D and E don't have a particular pattern, so it does not represent the autocorrelation. Means there is no autocorrelation. Error term DW, sorry, Darwin-Watson test statistics. In this, some things are in this test. Error term is normally distributed. Second, there is no missing observations. And the third, regression model include intercept term. Fourth, it is used only for first order autocorrelation AR1. Fifth, regression equation does not include lagged value of dependent variable. For example, yt equals to alpha plus beta 1 x1 plus beta 2 yt minus 1 plus ut. Here yt minus 1 is a lagged value of dependent variable. So this regression equation is not included for the testing in Darwin-Watson test statistic. Run test. Run test, it is similar to the run test for non-parametric. First model fitted using the OLS method and then residuals obtained. Residuals may be positive or negative, and arrange these residuals in ascending order with the time. The number of runs formed by positive or negative. The residuals are random. And number of runs are formed by positive or negative. So, and we wish to test the null hypothesis H0. Residuals are random, no autocorrelation. It means there is no autocorrelation. Against the alternative H1 means residuals are non-random, means there is existence of autocorrelation. Too few runs RL, too many runs RU. Okay, RL is too few runs. The number of runs you will have, then the RL is the too few runs and RU will be the too many runs there, and this indicates that sequence is non-random. N1 and N2. N1 is the number of positive signs and N2 is the number of negative signs, and capital N equals to N1 plus N2. Large samples test. It is approximated by normal distribution. For large sample test, it is approximated by the run test is approximated by the normal distribution. Expectation of r equals to 2 n1 into n2 by capital N plus 1, and variance of r equals to 2 n1 into n2 in bracket 2 n1 into n2 minus capital N by n square in bracket n minus 1. Heteroscedasticity. In a linear regression model, yi equals to alpha plus beta xi plus ui, where ui is stochastic disturbance term, xi is independent or explanatory variable, yi is dependent variable. I takes value from 1 to and so on small n. Variance of ui equals to sigma square mu, which is constant for all I takes value 1 to 3 and so on small n. This assumption is known as the assumption of homoscedasticity. If all the disturbance terms do not have the same variance, this condition is non-constant variance is known as heteroscedasticity. The graphical representation. Homoscedasticity shows the all the variances which are draws are the same size and lie on the straight line. So variance remains constant, and in heteroscedasticity, when the variance increases, then the graph is increases, and the when variance is decreases, graph is decreases. Matrix notation. In linear regression model, y underscore equals to x beta underscore plus u underscore, where underscore represent the column vector. Variance covariance matrix is represented as covariance underscore equals to expectation of u underscore into u dash underscore, u underscore dash, which is expectation in matrix expectation of u square, expectation of u1 u2 and so on, expectation u1 u into expectation un. In the nth row, expectation un into expectation u1, expectation un into expectation u2 and so on, expectation un square. Expectation ui square equals to sigma I square, which is variance of ui for all I takes value from 1 to and so on n. Thus the covariance equals to here expectation ui into uj equals to expectation ui into expectation uj, which is equals to 0 for all I not equals to j. Thus covariance u underscore equals to sigma 1 in the first row, sigma 1 square 0 0 and so on 0, in the second row 0 sigma 2 square and so on 0, and then in the last row 0 0 and so on sigma square. And variance covariance matrix in the presented heteroscedasticity. In the presence of heteroscedasticity, this is the variance covariance matrix in the presence of heteroscedasticity. Means these are not autocorrelated, but heteroscedasticity is present means diagonal elements are not same and non-zero, but non-diagonal elements are zero. Diagonal matrix with unequal elements in the principal diagonal. Consequences of heteroscedasticity. If we use OLSC in heteroscedastic model, first OLSC estimates are unbiased. Yi equals to alpha plus beta xi plus ui, I takes value from 1 to and so on, and OLS estimate of beta equals to sxy by sxx, that means summation small xi into capital yi by small xi square, and beta cap equals to summation takes from 1 to k 1 to n, I takes value from 1 to n, ki capital yi, which is equals to beta plus summation ki ui. We may assume here ki equals to xi by summation xi square, and summation ki xi equals to 1 summation ki equals to 0. Expected beta cap equals to beta. It is unbiased estimator of beta. Alpha cap equals to y bar minus beta cap x bar square. So our expectation of alpha cap equals to y minus expectation of beta cap into x bar, which is y minus beta x bar, which is alpha. So alpha cap is unbiased estimator of alpha. Variance of OLS estimators will be incorrect. Simple linear regression model yi equals to alpha plus beta xi plus ui. I takes from 1 to and so on n. Since beta cap equals to beta per summation ki ui I from 1 to n, and variance of beta cap equals to expectation of beta cap minus beta ka whole square equals to summation ki ui square expected ui square plus summation j from 1 to n I from 1 to n I not equals to j ki kj expected ui uj. Expected ui uj equals to 0 for I not equals to j, and ij takes value 0 1 2 and so on n, since there is no autocorrelation. So variance of ui equals to expected ui square equals to sigma I square, which is equals to fxi. Thus variance of beta cap equals to summation I from 1 to n ki sigma I square is not constant but depends upon the value of xi for all I takes value from 1 to small n. Here variance ui equals to expected ui square, which is equals to sigma square I, which is unknown. Hence we have to estimate it from the sample data. Hence we have to use the residual ei estimate of the disturbances ui's. Estimate n variables sigma 1 square, sigma 2 square cap and so on sigma n square cap from n observations x1, x2 and so on xn. That is, we have to estimate the variance from one observation only. Therefore, this estimation is impossible because we can't estimate variance from one observation. The third is OLS estimators are inefficient. Consider simple linear regression model yi equals to alpha plus beta xi plus ui I from 1 to n so on n. Beta cap equals to beta plus summation ki ui I from 1 to n. Ki equals to xi upon summation xi square. Beta cap minus beta ka whole square equals to summation ki ui square plus summation j from 1 to n I from 1 to n ki kj ui uj. Expected ui uj where I not equals to j equals to expected ui into expected uj equals to 0. So variance of beta cap equals to summation ki square I from 1 to n expected ui square, which is equals to sigma I square by sxx. Under the homoscedasticity assumption, variance of ui equals to expected ui square equals to sigma square for all I. So variance equals to sigma square by summation xi square, which is sxx for all I. Under the heteroscedasticity assumption, let us consider variance of ui equals to expectation ui square equals to ki sigma square for all I 1 2 and so on. So variance of beta cap equals to ki sigma square by summation yes small xi square, means summation xi square by summation ki, summation xi square into ki by summation xi square ka whole square. So it will be variance of beta cap equals to sigma square is by sxx into summation xi square ki by summation xi square. Since summation xi square by ki by summation xi square is greater than 1, that is ki and xi square are positively correlated. Variance of beta cap is greater than variance of beta cap when the presence under heteroscedasticity assumption. Variance of beta cap is greater than the variance of beta cap under homoscedastic assumption. Test for the heteroscedasticity or Park test for the heteroscedasticity. There are Park test, Glaser test, Spearman's rank correlation test, Goldfield quantity test, Burson Pagan Godfrey test. Park test. It is based on the assumption that heteroscedastic variance is function of explanatory variable xi, which is the second number of the, here it was, we have taken variance of ui equals to expectation ui equals to sigma I square equals to fxi ऐसा, based on the assumption that heteroscedastic variance is a function of the explanatory variable xi, sigma I square equals to fxi. So that is variance of ui equals to sigma I square equal to expectation ui square equals to fxi, which is equals to sigma square xi to the power beta e to the power vi, which is stochastic disturbance term. That is sigma I square equals to sigma square xi to the power beta e to the power vi, taking log on both sides, where I from 1 to n is small n. Take log on both sides, variance of log sigma I square equals to log sigma square plus beta log xi plus vi log e, which is 1. So sigma I square is unknown. He suggested ei square, an estimate of sigma I square. According to him, if beta is the above regression is turns out to be statistically significant, if beta in the above regression is turns out to be statistically significant, it would suggest that heteroscedasticity present in the data. Okay, means in the log sigma I square equals to log sigma square plus beta log xi plus vi. If the beta in the above regression is statistically significant, it means there is presence of autocorrelation. It would suggest that heteroscedasticity, it would suggest that it is test of heteroscedasticity. It would suggest that heteroscedasticity present in the data. Glaser test. Glaser test. It is similar to the Park. Glaser suggested that several functional forms. Glaser suggested several functional forms after obtaining the residuals EIs from the OLS estimation. Glaser used following functional form to detect the heteroscedasticity. Mod of ei equals to alpha plus beta xi plus vi. Mod of ei equals to alpha plus beta root xi plus vi. Mod of ei equals to alpha plus beta by xi plus vi. Mod of ei equals to alpha plus beta by root xi plus vi. Mod of ei equals to under root alpha plus beta xi out of root plus vi. Mod of ei equals to under root alpha plus beta xi square out of root plus vi, where vi is error term. If the beta in the above regression model is turns out to be statistically significant, it would suggest that heteroscedasticity is present in the data. This test has the following drawbacks. First, error term vi in the above functional form itself may be homoscedasticity. May be homoscedastic. Itself may be homoscedastic. And the second, last two functional forms non-linear parameters because of root, means it is not non-linear parameters, can't be estimated by OLS estimation. So it can't be estimated because there is non-linear parameters, so it can't be estimated by OLS estimation. Spearman rank correlation test. It regression model yi equals to alpha plus beta xi plus ui. I takes from 1 to n so on n. Residuals ei is the estimate of disturbance term ui's. Steps: first, fit the regression line and obtain the residuals. Second, calculate mod of ei and arrange the both mod of ei and xi on yi in the ascending order with time. Third, obtain the ranks of mod ei and xi or yi cap, both rank of mod ei and xi, and compute di, which is rank of mod ei minus rank of xi. Here summation di I from 1 to n will be 0. Fourth, Spearman rank correlation coefficient is obtained as r equals to 1 minus 6 summation di square by n into in bracket n square minus 1, where small r takes value from minus 1 to 1, where n is number of observations. Fifth, if rho equals to population rank correlation coefficient, test the null hypothesis. If rho equals to the population rank correlation coefficient, then test the null hypothesis h naught rho equals to 0. That means heteroscedasticity, there is no heteroscedasticity, and h1 rho not equals to 0 means there is presence of heteroscedasticity. Sixth, under the h naught, use the test statistic t equals to r under root n minus 2 by under root 1 minus r square, where it follows t with degree of freedom n minus 2. If calculated mod t is greater than tabulated mod t alpha by 2 comma n minus 2 degree of freedom, then h naught is rejected. Goldfield quantity test. Consider the linear regression model yi equals to alpha plus beta xi plus ui I from 1 to small n. This test is based on the following assumption. First, number of observation is at least twice the number of explanatory variables. Second, heteroscedastic variance sigma e square is positively related with explanatory variable. Third, sigma e square is directly proportional to xi square for all I, the square of the explanatory variables, that is sigma e square equals to sigma square into xi square, where sigma square is a constant for all I. Goldfield test is carried out in the following step. First, arrange the values of xi ascending order and omit c central value. Divide the n minus c observations in two equal parts, having n minus c by 2 observations in each. Second, one has a part smaller values of x, while other is the part for large values of x. Third, fit a separate OLS regression for both the parts. Residual sum of square for each part. Fit the separate OLS regression for both the parts. We have to fit the separate OLS regression and residual sum of square for each of the part we have to find या calculate. Fourth, summation E1 square equals to RSS for the part of smaller values of x is the residual sum of square for the part of the smaller values of x, and summation E2 square is the residual sum of square for the part of the larger values of x. Calculate f equals to summation E2 square by degree of freedom upon summation E1 square by degree of freedom, where degree of freedom equals to n minus c by 2 minus k, where n is total number of observations and c is the number of central observation omitted. K is the number of parameters including constant terms. Fifth, test the null hypothesis H naught UIs are homoscedastic. Variance of UI equals to sigma square for all I. H1 UIs are heteroscedastic, means variance of UI equals to sigma I square for all I. Calculated F is greater than tabulated F with degree of freedom n minus c by 2 minus k comma n minus c by 2 minus k. Then H naught is rejected, that is heteroscedasticity is present.